Well, hello everyone. Let's talk about 5-6, finally the fundamental theorem of algebra. The key concept behind the fundamental theorem of algebra is we're going to use it to be able to write or solve, basically, polynomial functions that could have real roots and could also have imaginary roots. Sounds pretty complicated. In fact, it is pretty complicated. I won't sugarcoat it. But what I will do my absolutely best to do right now in this video, and don't forget it's rewatchable, take your time with this, is kind of connect this to 5-5 as best I can and show you how you can, what the connection is between those two and how you can make this work a pretty straightforward job. Okay, so before we even look at a single problem here on 5-6, I'm going to flip back to your 5-5 notes. You do not need to go and grab your 5-5 notes, but I want you to take a look at this here on the screen here. I'd like you to take a look at problem number 4. We already did one over here on that got it problem. I'm going to come back here to it in a second. But look at the way problem number 4 is being asked. They're asking you, what is a third degree polynomial that has roots of -4 and 2i? And do you remember what we did with that? What we did with that is we knew that if -4 was a solution and 2i was a solution, we knew that also that -2i was a solution. So we knew that these three guys right here had to be factors of the correct polynomial. And if I scroll down here, this is the correct polynomial. We multiplied. If you grabbed your note sheet at this point in time, you notice we did a whole heck of a lot of work in there, which I'm not going to show here because it's really, quite frankly, not really all that relevant to what we're going to be doing here in 5-6. What I want you guys to understand about really what we're doing about 5-6, which if you try to do it on your own is a very, very, very intimidating lesson, a very intimidating read, is pretty much to see what we're just doing right here. I'll go even one step further. Let me erase this. And I'm going to take that concept right here and see how the roots are -4, 2i, and then wouldn't we also have to have -2i as a root, those three solutions right there. We took those three guys and we went from here and we went down to there. This is pretty much what 5-5 was all about. Here's what you are doing in 5-6. In 5-6, your job now is to start here and be able to give me those guys right there. Is essentially going in reverse. Okay, so what Mr. Cook is going to do, as quickly and as succinctly as I can, which means with little fluff, little busy work, getting quick and easy answers, I'm going to show you how you can do this work for 5-6, giving you a polynomial function, how you can get these answers. Now let me first point out something here, the first easy step that everyone in these when you're doing these problems should always start with doing. Are you listening? This part's important. When I give you a problem and I say, hey, give me all the solutions, and I say solve it, okay? The very first thing that you should do is you must graph it in your graphing calculator. You got to. You just have to. Okay? So I'm going to go to my graphing calculator. And what you see here is me already typed in, I've already typed in the function here, x to the third plus 4x squared plus 4x plus 16. Let me just double check to make sure I didn't make any mistakes. X to the third plus 4x squared plus 4x plus 16. Back, back, back. Oops, wrong direction. Sorry. Yep, looks good. All right. Now here's when you type that in, hit graph first. Now, your job, remember, your job is to find out where the zeros. If you go even further back to the work that we've been doing, when I was here, when I was with you guys in chapter 4, when you were solving quadratics, you could solve a quadratic by just figuring out where the graph crossed the x-axis. In other words, a solution to a quadratic was the x-intercepts, where the graph crossed the x-axis. And you see the x-axis is this horizontal guy right here. Looking at this graph of this cubic function, the third power here, we end up with a graph with 1 0, one real zero. Okay, if I go to my table to confirm where that one real 0 is. Looked like it was at -4, and sure enough, there's the confirmation right there. At -4, the y value is 0. Let that soak in a little bit when we go back to that page and we look at this right up here. Do you see how one of the solutions was -4? Right? That's not an accident. So that's why when Mr. Cook is telling you on 5-6 to start with the graphing calculator, the graphing calculator will give you every single time when you use the graphing calculator to start your work, that will, wrong button again, it will be able to give you the real solutions. If there is one real solution, there it is. Sometimes you're going to run across some problems and you'll have more than one real solution. We'll look at that in a moment. What the graphing calculator cannot do, what the graphing calculator will never be able to do, is the graphing calculator will never be able to give you any of the imaginary solutions. Okay? In other words, over here, 2i, -2i, you'd never be able to see those on that graphing calculator. But here's what you would do. Do you remember all this factor business that we just did right here? Here's one thing that we would know to be true. If we just figured out that that graph has an x-intercept of -4. We just found a 0, and that 0 is -4. So wouldn't this be a true statement about this polynomial function right here? Save myself some time, I'm going to pause it and write out the whole thing. So we would be in this position here. If x minus 4, x equals -4 is a solution, then x plus 4, opposite game, must be a factor. Okay? In other words, I could say that x cubed plus 4x squared plus 6x plus 16 could be factored into x plus 4 times some unknown factor. Okay? I could multiply these two guys together and I would get this. Now, if I were to ask you this question like this, suppose I gave you 2,736. Wouldn't you know that this would have to be true? Right? 2,736 would have to be 2 times something. And my question to you, as you tell the person next to you, is how would you figure out what that missing number was? Right? Pretty simple solution, right? To find that answer, all you'd have to do is take that big number there, that 2,736. Oops. There's a 3. And then just divide it by that 2. And then that answer that we get right there, that quotient, would be what was left over. Now, take the time machine. Let's go back to when we did synthetic division in 5-4. That at the time probably made no sense why we were doing it. What we are about to do is synthetic division. If this guy right here is a factor, then we can take this polynomial right here and divide it by x plus 4, and we'd figure out what goes in there. So, see the plus 4, I'd put in a -4, x to the third, so that'd be 1x to the third, 4x squared, a 4x, and a 16. Now, because this is a factor, watch what happens. We bring down that 1 because we're adding nothing to it. Multiply, -4, add those, you get 0. Multiply, you get 0 again. Add those, you get 4. Multiply that, you get -16, and sure enough, we get a remainder of 0. Take a look at that. That's the quotient right there, isn't it? And that quotient is a quadratic function. And that quadratic function, as it stands, the way it looks, would look just like this now, wouldn't it? It would be x squared. Grab a different color. Stick with me. It would be x squared plus 0x plus 4. So, if we are looking for zeros, then I know that x plus 4 times x squared plus 4 would give me this cubic trinomial right here. Okay? In other words, we found one 0. There he is. We are looking for those other two, remember, which we already had, which were these plus 2i and -2i. We could find that one pretty easy by looking at this guy right here. and just saying to ourselves the same thing that we did when we were dealing with quadratics, right? Green, x plus 4 times blue, x squared plus 4 would be equal to 0. So wouldn't this be a true statement? X plus 4 could be equal to 0, and then we could solve that quadratic by subtracting 4 from both sides. And then x squared equals negative 4. We would then take the square root of both sides. And remember, when you take a square root, you don't get just one answer. You get two answers. Do you see why I broke that apart into positive 4 times negative 1? Wouldn't that be, oops, you know what I forgot to do is forgot to take that square root, that square off there. There we go. Okay. Then we would have, blue please, 2. And then the square root of negative 1 would be, you guessed it, I, but remember we're forgetting plus and minus 2i. So those would be all of our solutions, plus minus 2i and negative 4. Okay, that's how that works. Okay, I'm going to pause the video and we're going to look at this example right here again. Okay, we have not even looked at 5-6 yet.